Alright, I wanted to make a video here to talk a little bit about how we can use Laplace transforms to solve environmental engineering transport problems. And so this technique is particularly useful when you're analyzing a series of well-mixed tanks. It can be used, it's very broadly applicable, but it's particularly useful, maybe the easiest way to solve the problem when you have multiple tanks in series. So I wanted to make a couple of videos to just kind of show you how to do Laplace transforms, and then I thought this might be helpful to understand how to solve the problem where you have lots of different reactors that are connected together. So let's start by just talking about what Laplace transform is. So Laplace transform. The basic idea with a Laplace transform is we're going to go from, so we're often trying to solve a problem that's a function of time. Laplace transforms are really good for solving problems that are a function of time when they're differential equations. What they allow us to do is they allow us to take the time derivative and make it go away. So we can take a problem, a differential equation where we have a derivative with respect to time, and turn it into an algebra problem. And most people would rather solve an algebra problem than a differential equation. So the way that this works is we're going to transform a problem from the t domain. So we're going to transform from, I'll put t in quotes, domain to s domain, which is sometimes called like the frequency domain. It doesn't really matter for us that it's frequency, but you can use this for problems where you have derivatives with respect to space, but it just tends to work better for problems with respect to time. You can use this for systems of differential equations. You can use it to take a partial differential equation that has a time derivative and turn it into an ordinary differential equation that doesn't have that. So it's really useful for a lot of things, but the key idea behind it is basically we're going to take a problem from the t domain and then move it into the s domain. So if you look in a math textbook, math textbooks will show you how to do things mathematically, but it's often hard to understand how to use them in practice. So I'll just put like math. It's going to say that we're going to go from like f of t to big F of S. This is the way it would often be written. There's lots of different places you might find this. And I have an example right here of a table of Laplace transforms where it shows us what a function is in t. So if I have f of t is 1 in the t domain, if I switch it to the s domain, it becomes 1 over s. Okay, and so the way that you do this is by doing an integral, and you can go look up how you would actually derive what the Laplace transform version is, but for our purposes here, you don't need to do that derivation. I'm just trying to focus on how you use these because I want you to think about how this is a useful technique to solve problems. But so this is a whole bunch of them. All right, so here again, big F and little f to solve these. In this, for environmental engineering, or it could be chemical engineering, I guess, but I'm an environmental engineer, so I'm going to say basically I'm often looking for the concentration at different times, and I'm going to write that instead of concentration with respect to time, I'm going to put C bar of S. So here C bar is in the S domain, like the big F, and then C is the little f here. So if you're going to do this technique, you're going to have to be able to use tables that look like this, and you have to understand how the T and the S and all these other letters turn into the things that you're going to see in the environmental engineering application. Okay, and so why would I want to do this? Really the key thing, if you look at this table, is it allows me to take a derivative, like here f prime of t, the derivative of f with respect to time, and I can get rid of that derivative, and I can rewrite it in this s domain using the initial value of f. And so this, this works really well for for problems where t is the derivative, because those are usually, we have an initial condition. And so I can rewrite it that way. And then once I do this with a differential equation, I can actually just do algebra. Okay, so c of t is going to go to c bar. This is the way that I'm going to write it. You could use upper and lowercase c, but it's really hard to tell the difference between an upper and a lowercase c. I think the bar is easier. Some books might actually write f and f bar, whatever. So anyway, the idea is we're going to take our differential equation that's a function of concentration, and we're going to turn it into an algebra equation with this c bar term. Then we can solve that for c bar, and then we can turn it back into the t domain, and we don't actually have to do any sort of integration, or a lot of things that make differential equations kind of hard. So I'll just put quickly like our strategy: transform c of t to c bar of s. That'll be the first step. Solve for c bar of s, and then invert. So then we have to do the inverse Laplace transform, c bar back to c of t. C bar of s, let's say, back to c of t. This is the basic idea. Okay, so let's do an example. This is the easiest way to understand it. So again, the idea here is we're getting rid of our derivatives. We're going to do some algebra, and then we have to rewrite the c bar equation in a form that we can find in our table to solve it. So I'll do an easy example in this video, and then I'll make another video where it's a little bit harder, and then another one that's a little harder than that. So here, this is a problem you would often see. We have dc by dt is equal to minus q over v times c, and c at t is equal to 0 is c0. Now this is a problem that we would see all the time in environmental engineering, where we're looking at a well-mixed tank, and well-mixed tank here, and we have a flow going in and out, a flow rate q, it has some volume v, and then at t equals 0, c is c0. So basically we might have like a bunch of salt that's mixed up in here, and then we start flowing fresh water in and out, and then we want to know c is equal to what here at the outlet. Okay, so c is 0 coming in, so we have c0 in here in the beginning. We start the clean water in, and then this comes out. Initially it's going to have a bunch of salt, and then it's going to go down. And this is the differential equation that would describe that. Okay, so we have to know how to connect this physical idea into this equation. That's one part of the problem. We can then solve this one. It's not too difficult to solve it by, you can move the c over here and the dt over there and integrate. We could do it that way. Yes, I could do it that way, but let's think about how we would do it with Laplace transforms. So what we're going to do here is take Laplace. So L, this is how we're going to write it with like a curly brace of dc by dt has to equal to L of negative q over v times c. And so one of the properties of a Laplace transform is if something is a constant, then I can take it outside. So again, looking at an equation like this, it's very important that you understand the difference between these different kinds of variables that are here. This is a problem with math, again, where they would write this f, and they would write f of x, and it's not obvious what f is. It's not obvious, what f translates to in a real problem. It's not obvious what x is, all these sort of things. So here, c is what we're trying to find. We want to be able to predict the concentration out here. So c is our dependent variable. It's the thing we're trying to predict. T is the independent variable. We're trying to figure out what c is as a function of t. And then q and v are parameters, which means that they're a constant. So when we do the Laplace transform, we're going to be going from concentration as a function of time to concentration as a function of s. And so our independent variable is going to go from t to s, and our dependent variable goes from c to c bar. Q and v are just constants, so they're just kind of along for the ride. So one of the properties of Laplace transform is that constants can be taken outside. So really this is just negative q over v times the Laplace transform of c. And so what we have to do now is go and look this up. So if we go into our table, f prime of t is f times f of s minus f little f of 0. Okay, so this is, so you find a table of Laplace transforms like this, and you have to know how to use it. If you had a second derivative or a higher order derivative, it gives you a formula here you can use to write that out. So dc by dt is then, so c here is like my f, and so we said we're going to write c as c bar, and so it's c bar times s minus c at t is equal to 0. Okay, so that is s times big F of s minus f of 0. So my big F is going to become c bar, my little f is going to become c, and then t and s are the same in this situation. Okay, and then on the right hand side I'm going to get my negative q over v, and the Laplace transform of c is just c bar, so that one's not too hard. And remember here that c at t equals 0, we have this initial value, and it's c0. And c0 likewise is a parameter, it's a constant, so that makes it something that just kind of goes along for the ride. Negative q over v times c bar. Okay, so now I've taken this differential equation, kind of hard to solve, and turned it into an algebra problem, much easier to solve. So I can move this term over here, s plus q over v times c bar is equal to c0. And then c bar is equal to c0 divided by s plus q over v. Okay, so now this is my solution in Laplace transform domain, which is not what we want. We want it in the real time domain. So now what we have to do is we have to invert this. So we need to invert, so L inverse is how we're going to want to write that of c bar is equal to L inverse of c0 over s plus qv. So what we have to do is we have to find, this one is, it's pretty easy. The Laplace inverse of c bar is just c, because we did that one before. So this is going to give us our c of t, and now we have to figure out what function is going to give us this as a Laplace transform. So the c0 is multiplied here, so I can actually take it outside, and so then I'm just left with looking for 1 over s plus some constant, 1 over s plus a constant, and I need to find that. So I can go back to my table here, and if you look up here at the very top, you'll see that 1 over s minus a is e to the at in the real domain. So 1 over s plus q over v is going to be e to the minus q over v times t. So we get c0 e to the minus q over v times t, and we're done. So this probably about the same amount of work to do it in Laplace transform as it is to integrate it. Maybe it's even a little bit more work, but for other problems this technique can be very useful. And so I'll do another problem in a different video where we do something a little more complicated.